Hello, and welcome to this webinar series on model-based design for DO178C software development. This will be a 9-part webinar series that takes an example from a textual requirements document all the way through to fully verified and validated software running on a target processor. Necessarily, that's a lot of information, and so we've decided to split this into a couple separate sessions to make it a little easier for the audience to watch. The agenda is very lengthy. As you can see, things are divided into basically two major topics. So the first would be development and verification and validation of the model. This will be the first section, and this section is actually, I would say, the more important. As we'll see, that kind of the outcome of the code, the automatically generated code, and a lot of the verification and validation that we do at the code level is actually reuse of some of the activities that we do at the model level. The other thing that's worth noting is this webinar series is going to focus on software development, which is the DO178C standard. However, there's also DO254, which is the related hardware standard, so developing ASICs and FPGAs. All the things that we talk about for development and verification and validation of the model also works if you're developing HDL, VHDL, or Verilog. The differences just come in kind of in the code generation and then some of the downstream processes. So all of the stuff that we talk about at the model level is certainly useful both for DO178C and for DO254 workflow developments. So before we kind of get into the workflow itself and all the details, it's typically useful to kind of motivate this discussion. When I was in industry, I had a lot of experience where the software team were often the ones who were blamed for projects missing their deadlines. It was kind of always the common saying that software is always the long pole in the tent. It always takes the longest, so on and so forth. So Venture Development Corporation, who provided the information on this slide, went out and surveyed a bunch of software engineers in industry and essentially just asked them, why is it that you tend to miss your software deadlines? And so, of course, the most common answer, if you ask a software engineer, why did you miss your deadline? The software engineer is going to say, well, no one gave me the choice of what the deadline should have been. All right, which is probably what I would have answered if somebody asked me this question too. And so, indeed, that was the most common answer. However, the next two are actually the more interesting. So the next two most common answers were changes in specifications and inadequate specifications. So these changes in specifications, this would be if you've ever been working on a software project and you've been going along, developing your software, and then all of a sudden the customer or your manager comes by and says, hey, you know what? Instead of this software doing this, we need it to do this instead. All right. Typically, that's a major blow to your schedule because it can sometimes involve quite a bit of rework. And so again, this happens very, very often. So this was the second most popular response. The third, inadequate specifications. So this would be either I'm developing some software and at the end I test it and then somebody says, well, hey, this doesn't work. And then you say as a software engineer, well, of course it doesn't do that because you didn't tell me it was supposed to. So that would be an example of kind of inadequate specifications or missing requirements. And the interesting thing about these two responses is that they actually kind of get at the core reasons why model-based design is as valuable as it is and allows us to develop software in such a more efficient manner. So kind of taking that understanding of, where the requirement or where the errors or where the reason that we miss. So taking into consideration that the second and third most popular answers for why we tend to miss our software deadlines had to do with our specifications or our requirements. It's safe to assume, and I think most software engineers would agree with this, that most of the errors in a software development process are introduced in the requirements phase. Now, this slide talks about kind of the costs related to detecting errors. And again, this is a very well-known trend throughout industry. Basically, what this slide is saying is, the later in the process you detect an error, the more expensive it is to fix, right? And that makes a lot of sense. If I read a requirement and I understand, hey, that requirement's not complete, right, or not testable, it's easy for me to then just kind of change the text of that requirement. On the other side of the spectrum would be I'm on the actual vehicle and I'm doing testing or out doing maneuvers or something like that, and all of a sudden I find an error, right? If you wait until that phase, say the deployment phase would be the absolute worst, where you find an error, the cost to fix that error is very, very high because you have to go back and do the root cause analysis of where that error comes from. And again, typically it comes from the requirements. And that requires you to alter the requirements, alter the design, alter the code, and then redo all of your testing. And necessarily that's much, much more expensive. And so what we see is that model-based design actually provides the most value because it recognizes these kind of two opposing trends, that most of the requirements are introduced early in the process and not detected until later in the process. All right? And model-based design is all about using the model and the ability to simulate, right, to detect errors earlier in the process, therefore making everything kind of a lot less expensive. So what this particular slide shows is exactly that. So this is data, ROI data, return on investment data, that we have collected from many, many different of our customers in the aerospace industry. All right, and we've averaged those all out to kind of come up with some industry standards as much as you can for things like pricing and labor rates and all that kind of stuff. So we've come up with these kind of averages, again, to protect all of our customers' proprietary data. And we've run it through kind of this ROI framework to be able to kind of estimate the expected return on investment for an aerospace project, software development project of a certain size. And so, of course, if you're trying to justify to your management, hey, we should be doing more Simulink and automatic code generation, then these big numbers like 62% cost savings, 530% ROI are the numbers you want to focus on. But for this discussion, it's actually the shape of this that is the most interesting. Typically, the assumption about model-based design is that the savings comes from automatic code generation, right? Which is, a valid assumption. It's a lot quicker and faster and cheaper for me to develop a model and then be able to hit a button and get embedded software out versus developing a model and then handing it to a software engineer and allowing them to then write by hand, say, the embedded software. Not only is that more time consuming the first time, but then think about when you find errors and you have to do regression testing. Every time you have to go back and rewrite requirements or make changes in the design, you have to redo that software generation process. And so actually one of the keys that we're going to see is that automation, not just in code generation, is a huge player in the efficiency and cost savings that you get in model-based design. So again, automatic code generation, is it a big cost savings task? Yeah, absolutely. You can see there's certainly value represented by the red bar in the coding phase here. That is the realization of using automatic code generation. However, we also see that the size of the savings in the coding phase is actually very small compared to the savings that we get with model-based design in the requirements phase, which is this big red bar on the left, and the testing phase, which is this big red bar on the right. Now, this savings in the requirements phase, right, this is exactly what we were talking about with those previous slides. So the idea is that if most of the errors are inserted into the project at the requirements phase, right, the ability to simulate, run test cases against an executable design specification, detect errors in the requirements, detect missing test cases, detect unintended functionality. That's all of the value that you get by actually pressing the play button in Simulink. Okay, so people always ask me, what's my favorite feature in all of the MathWorks tools? I don't know about favorite, but I do know for sure that the single most valuable function that the MathWorks has ever created is the play button in Simulink. And it's really through doing that simulation that you can achieve this big red bar on the left. The big red bar on the right, again, is a lot about automation. Okay, so the MathWorks tools give you a lot of capability to automate many different tasks. This one is specifically about automating your testing. And more than that, it's not just about automating testing at the model level, but it's also about automating testing at the code level and achieving test case reuse. So the idea would be that rather than having several different engineering environments, the MathWorks tools for design and analysis, a C or C++ based environment for software testing, and then a hardware in the loop lab for hardware in the loop testing, right? Where all three of those different environments have their own versions of test cases and execution and all that kind of stuff. right? A lot of this big red bar on the right is about the ability to kind of commonize those engineering environments across those different engineering disciplines. The idea being that if I can write test cases based on my requirements once, if I can use that same version of the test cases to test my model, to test my software compiled locally, or to test my software running on an embedded processor, right? The ability to automate not just the testing in each of those environments, but reuse those test cases across those three environments is really where this big red bar of value on the right comes from. Okay, now in order to achieve this kind of value, right, then there's certain things that you have to be succeeding with respect to the usage of the MathWorks tools. And so this is a slide that we like to use with our customers to kind of discuss, how mature they are with our software, basically how much of the maximum value they're actually getting. So just to give you kind of some perspective, and I think it might be an interesting thought exercise for you to go through yourself to try to figure out where you and your project are on this grid with respect to our tools. So just to give you a little bit of context, right? If you say construct MATLAB code or Simulink models, but then you don't, maybe you run them once, but you don't generate code with them or anything like that, that would put you in this kind of lower left corner of design modeling. If you say build Simulink models, but you never execute them, you simply generate code from them, and then you execute that generated code in some other environment, that would put you in this lower right-hand corner, what we would call model-based programming. Okay. If you build big system-level simulations in MATLAB and Simulink, so you're running if you're a controls engineer, you can think of this as running big closed-loop simulations, vehicle-level simulations, system-level simulations, and you're doing a lot of analysis, and you're tracing test cases back to requirements, and you're doing rigorous testing with that big closed-loop simulation, that would put you in this upper left-hand corner. Okay. And then to achieve that value that we saw in the previous slide, you need to be in this upper right-hand corner, right? What we would call fully leveraged model-based design. So this includes all of the rigorous verification and validation, automated testing, test case reuse in the code environments, as well as automatic production code generation and code verification and validation. So if you're doing all of that kind of stuff, that puts you in this upper right-hand corner, which is where you kind of maximize the return on investment with our tools. So of course our goal is to help everybody understand what they need to do to get into this upper right-hand corner so that they are achieving maximum value with our tools. And so that's what we're going to go through in this series of webinars, is basically a workflow that fully describes what it would take to be in that upper right-hand corner. All right. So that's the idea, is that the more things that you do with the model, right, the more you leverage that model, the more value you're going to get out of our tools. All right. Now, before we can talk about the workflow itself, we have to do a little bit of terminology, just to make sure that we're kind of all speaking the same language. Unfortunately, the definitions of some of these terms are a little bit vague. People tend to have different definitions, so I just need to make sure that we're speaking the same language, and when I say these things, you know exactly what I mean. So the first are verification and validation. These are, of course, very, very big terms out in industry. Now, just to be clear, when I say verification, I mean, did I do the design right? Did I do it correctly? When I say validation, I mean, did I do the right design? Did I build the right thing? Okay. These are consistent with kind of the DO 178C definitions of these terms, at least in the US. All right, some other common terms that I'm going to use: traceability. So traceability is really a documentation activity. It essentially is about every time I create something new, I need to trace it back to where it came from. All right, and so you might hear people talk about top to bottom and bottom to top traceability, or bidirectional traceability. Essentially what that means is that when I create something new, I need to trace it back to where it came from. In other words, make sure that it does everything it's supposed to do. And then the other side of it is, not only does it have to do everything it's supposed to do, but I have to ensure that it's not doing anything extra. It's not doing anything that it's not supposed to do. Okay, so that's what we mean by that top to bottom and bottom to top traceability. Another common term you're going to hear is kind of conformance to standards. Most software engineers are very familiar with the idea of coding standards. We'll talk quite a bit in one of the later webinars about coding standards and kind of what they really are and where they come from. But for now, it suffices to just say, for all the same reasons that we have coding standards, when we start to do model-based design and we're working with the model, particularly if we're going to automatically generate code from the model, then we also need to have modeling standards. Right? So again, in one of the later webinars, we will go through in depth kind of how to create a modeling standard and what that means and how that's related to our coding standard. All right? Another common term, testing. Everybody understands testing. Everybody who develops software understands testing. There's a lot of different kinds of testing. There's white box plus testing, black box testing, gray box testing, structured testing, unstructured testing, structural testing, functional testing. So there's all kinds of different testing. Within the context of the workflow that we're going to describe, there's really only one kind of testing that I care about, and that's functional testing, or requirements-based testing. Okay, so if I say functional testing, I mean requirements-based testing. The idea being that the test cases themselves are based on the requirements. So somebody read a requirement, and then based on that requirement came up with a scenario to evaluate whether we're meeting that requirement, and then expected outputs. And those expected outputs are based on that requirement. So that's what I would call functional testing. And actually all of the testing that we're going to talk about in this workflow is functional testing. All right. The last thing that I'm going to talk a little bit about is proving. Proving is really the application of formal methods. The best way to describe this is if you think about executing a test case, right? If I have a test case based on a requirement, it has inputs and expected outputs. If I execute those inputs against my model or my code, and then the outputs of the model or the code meet the expected outputs based on my requirements, what I have really shown in that scenario is that for that one specific set of inputs, my model or my code is behaving according to my requirements. Proving is about answering the question, how do I show that my model or my code will always exhibit the desired behavior regardless of the inputs that it gets? In other words, I need to show that my model or my code is correct for every possible permutation or combination of inputs that it could ever see. And that's a very, very difficult problem if you just do testing, right? Because in order to show that with just testing, you would have to come up with all of those test cases. You'd have to come up with every conceivable combination of inputs that that algorithm could ever see, execute those, and check that the output meets our expected output. Okay? And there's no way that realistically you have the time in your program schedule to try to do that level of exhaustive testing. All right? So proving is all about answering that same question in a much more formal way. So instead of coming up with inputs and expected outputs, right, if we can give those expected outputs, or if we can understand that requirement and give it some sort of mathematical meaning, then there are situations in which it's possible for us to take the model or the code or the algorithm in question and actually do a closed form mathematical proof to show that the math represented by the code or the model will always exhibit the mathematical behavior that represents the requirement. All right, and so that's kind of in general what the application of formal methods or what proving is all about. And again, we'll touch on this a little bit. It's quite a bit more advanced, and there's actually in DO 178C, there's a whole addendum now on formal methods tools because these are kind of growing in popularity and use throughout the industry. All right, so with all those definitions in mind, let's actually talk about the workflow. In this case, we're just going to talk about the workflow. We're not talking about any sort of specific tools or anything just yet. We're just talking about, what is a process that would kind of meet all of the expected rigor for something like DO 178C level A software development. Right? I mean, again, it's important to note that certifications like DO 178C, there's other ones in other industries that are similar with some subtle differences. So in the automotive industry, there's ISO 26262, there's IEC 61508. The thing about all of these kind of standards is that they're actually software development certifications. In other words, the idea is that you have to show that there is a rigorous process, and you followed that rigorous process to develop all of your software. So it's not something that you just check the code. It's not like a coding standard or certification, something like that. It's actually a software development process certification. All right. And the very key, especially for DO178C, is that everything has to be based on requirements. Okay, so it's all about requirements-based software development. All right. So anytime you talk about kind of a workflow associated with developing software for a standard like DO178C, it all starts from your requirements. Okay, your requirements are typically in a textual domain. There are some instances now where you can model requirements, so you can actually have models of requirements. This is a little bit more of an advanced maneuver. For the purposes of this particular workflow, we're going to focus on our requirements being textual requirements. In other words, they're actual text written in something like Word or Doors or Excel or some kind of textual tool like that. All right. Now, we have requirements. The very first step is that we need to validate those requirements. Okay, so remember, validation is, did I build the right thing? Okay, and so what this is really typically done as is a manual review of your textual requirements, particularly if the requirements, say for the component of software that we're focusing on right now, right, those requirements are going to be lower level requirements than, say, some system level requirements, right? So this validation step in that scenario is, again, a manual review where you're trying to understand if these lower level requirements accurately capture the intent of the higher level requirements, right? So again, this validation step is almost always a manual review of your textual requirements, okay? Then once we're sure our requirements are complete, consistent, and testable, the next step is to come up with a design, right? So the design is basically some expression of the algorithms that we feel will meet all of these requirements. Now, the design is something new. Every time we come up with something new, we have to trace it back to where it came from, all right? So in this step, what the traceability means is that we need to show that every single requirement is somehow satisfied in the design, and that there's nothing extra in the design that isn't linked back to one of the requirements, or in other words, isn't required or isn't something extra. Okay, so again, that's what we mean by that top to bottom and bottom to top traceability. All right. So we have the design, we've traced the design back to our requirements. The next step is this idea of conformance to standards. Okay. Now, how this actually gets done is highly dependent on the format in which the design exists, right? So if this is something like a Word algorithm description document or something like that, right? This could be as simple as, did we use the right template, right? It's all about making sure that this is something that's consistent with what everybody else comes up with, is readable, is reusable, so on and so forth, all right? Again, we'll see when we get into model-based design how this conformance step takes on quite a bit more meaning, all right? So after we've made sure that the design conforms to some kind of standard, the next step is a verification step. Okay, so we need to verify that the design actually meets our requirements. Right? Now, again, how you do this is highly dependent on what format your design takes. So in a very traditional software development process where the design is typically some kind of software description document or algorithm description document or something like that, this verification step is typically verification by review. So this would be where you sit with the design document and you verify it against the textual requirements. Okay, and again, this is actually where, when we looked at that ROI slide, this is where that big red bar on the left really comes from when we start to use the MathWorks tools. And again, that's all related back to the fact that Simulink has a play button, right? So as soon as this becomes a Simulink model instead of some kind of paper document, and we can press play, now this verification step, instead of being verification by review, can become verification by simulation. Okay, and that's a step that can be automated, and so that's where a lot of that value comes from. So we'll get into that on the next slide. All right, but for now, it just suffices to say that however you have to do it, there's some verification step. You need to verify that the design actually meets all the requirements. All right. Once we're sure that the design is complete and correct, it meets all of the requirements, then you have to come up with the source code. All right. Again, in a very traditional software development process, this would be where we hand that algorithm description document off to a software engineer, and they go off and write the embedded software. All right. Now, again, we've created something new. We've written a bunch of software based on a design document. And so the next step is a traceability step. We need to document that basically every line of that C or C++ code is related back to something in the design, and that everything in the design was implemented in that software. Right, so that's this traceability step. All right, so now we have the code, we've traced it back to our design. The next step is, again, this idea of conformance to standards. This is kind of our very typical, well-known, does this source code conform to our coding standard? All right, and again, we'll have a long conversation in a later webinar about coding standards and what this all really means. All right. Now, once we've kind of made sure that the code conforms to standards, the next step is, again, a verification step of the code against the design. And again, this is very commonly verification by review. Most often, this is what most project development teams consider their code reviews. Okay, so again, this is where you have a bunch of your peers sit in a conference room, you have the design document, you have the C code up on the projector, and you review this code to make sure that the code did indeed properly implement what was in the design. Okay, so this verification of the source code, this is, again, your typical kind of code review process. All right. Once we've reviewed the code against the design document, now we want to actually start testing the code. And to do that, we need to compile it, right? And I break this out as a separate step because in a process like a DO178C level A process, this compiler step is actually very important. There is a difference between me, say, compiling locally and running test cases on my desktop versus me compiling with an IDE and actually putting the object code on the target processor. For something like DO178C level A, you really want to do this as testing the object code on the target processor. All right. So the idea is that now we have the object code executing on the target processor, and there's really two steps. So one, we need to show that the object code on the target processor is functionally equivalent to the design. All right. So that basically these two things give us the same answer in every case. And if you do that successfully, then kind of by the transitive property, if the object code is functionally equivalent to the design and the design meets the requirements, you could say we're done. But again, for a rigorous process like a DO178C process, you actually need to repeat this requirements-based testing. So in the end, you actually need to show that the code running on the target processor actually meets our requirements. All right. So again, we'll see that these two instances of verification, this is really where that big red bar of value on the right comes from. If we can achieve automation and test case reuse here, that's how we can see that significant value in the testing phase. So again, this is just kind of an example workflow. It's tool agnostic, but this is kind of a very rigorous development process that would meet the needs of a certification like DO178C. So the next step is then to understand how the MathWorks tools would fit into a rigorous software development workflow like this. Now, the first thing you'll notice is the validation step of your textual requirements. Recall that this is typically accomplished by a review of your textual requirements. So there's not actually that much that the MathWorks tools can do to help you with this particular task. However, from then on, we should be able to greatly assist. The second big thing you'll notice is that now, instead of the design, I'm very specifically saying that this is the model. And I mean that to be even more specifically, not just any model, but Simulink models and stateflow models. So the idea would be that with a model-based design workflow, you would look at your textual requirements and then based on those, come up with a design using Simulink and stateflow. Now, another thing that's going to be a recurring theme throughout all of this is this idea of automatic report generation. So not only is it important to define a rigorous software development process like this, but it's also essential that you document that you actually followed this rigorous process. We understand, again, in that theme of automation, that writing documents by hand is a very time-consuming process, especially if you have to go through this whole process many, many times, which inevitably you will. So anytime that we can automate any of that report generation, there's a good deal of time and money to be saved in that. So specific for this task, the key report would be the System Design Description document, which is this SDD. This is a built-in report that's included with Simulink Report Generator. And the intent of this report is to be a very, very complete document of everything that's in your Simulink and stateflow model. So essentially, this report will include all information that you would need, such that if all computers in your entire company crashed, from this one paper document alone, you should be able to reconstruct your Simulink model to completion. So that's the intent of this. If you really, really need to have, for some reason, a paper document of your design, the SDD is a very good report to satisfy that requirement. Now, once you build your Simulink model, right, which is the expression of your design, we built something new, so we have to trace it. And the tool that we have that can help with this is Simulink Verification and Validation. Simulink Verification and Validation shows up really 3 times in this process, the first of which is this RMI, or the Requirements Management Interface. What RMI allows you to do is actually create hyperlinks between the basic constructs of your model and your textual requirements. So for example, you could go to any block in your Simulink model, right-click on it, and create a hyperlink from that modeling element to your textual requirements. Likewise, we also support what we call bidirectional traceability, which means that not only can we create a link from the model to the requirements document, but in some cases, like Doors, Word, and Excel, we can actually create links in those documents to bring you back into the Simulink model. So this is how we can support that idea of top to bottom and bottom to top traceability. So after we've built the model and we've traced the model back to our requirements, the next step is this idea of conformance to standards. Now, I mentioned before, when you're doing model-based design, the modeling standard becomes very, very important. And really, there's 2 reasons for that. The first is that the modeling standard becomes a way that we ensure that everyone on a development team is working in a consistent design environment. So within Simulink, what this typically means is just ensuring that everyone who's building Simulink models is using things like the same solver options, the same sample times, the same diagnostic settings. And then more subtle than that, and kind of more user-specific, would be using the right block constructs with the right options. And so that's part of the modeling standard. Now, related to that is the second reason why the modeling standard is so important, which is that the modeling standard actually is how you enforce the coding standard on the automatically generated code. So what happens is, if you want the automatically generated code to conform to some kind of coding standard, the way you enforce that is through the modeling standard by saying use these blocks with these options in this way with these code generation settings, because we know that that will then provide automatically generated code that conforms to the desired coding standard. So the modeling standard becomes very, very important when you start talking about model-based design. Now, how can the MathWorks help with that? Well, part of Simulink is what's called the Model Advisor. Okay, and the Model Advisor is a static rules checker for Simulink. Now, I already mentioned Simulink verification and validation, so that was what gave us that requirements linking capability. The other thing that it provides is a bunch of extra capability in the Model Advisor. Okay, and there's really, again, kind of 2 major classes of this. So first and foremost, if you have Simulink verification and validation, we ship a bunch of extra folders of checks that the MathWorks has authored, kind of specific to certain tasks. So one of these folders of extra checks is the DO178C/DO331 folder of checks. So these are a bunch of modeling standards that and checks that the MathWorks has authored that we recommend if you know that you're working in an environment like a DO178C software development environment. Now, that obviously doesn't mean that you have to follow those rules. They're just general recommendations that we have come up with as we worked with many customers who are doing this. Perhaps more important than the extra checks that the MathWorks ships is with Simulink verification and validation, you have the ability to write your own custom checks. And this is something that I guarantee and eventually you will want to do. So again, think of the coding standard. As you go through this process in an iterative way, you're going to, collect lessons learned, right? And if you think about standards, coding standards or modeling standards, what they really are collections of lessons learned. So let's say you have a Simulink model, you generate code. In the code, you see something that doesn't necessarily conform to your custom coding standard. So then you're going to go through an exercise to understand what you have to change in the model so that when you do generate code, it does conform to your coding standard. And whatever it is that you learn as far as what you had to change in the model, that's a good opportunity to write a custom model advisor rule, which essentially just makes sure that everybody else on your team who's going to be doing the same thing doesn't make the same mistake you did. And so you ensure that what you learned about how to ensure that you get good generated code, right, can then be automatically passed on to everybody else in the team who's going to be automatically generating code from their models. So that ability to write your own custom checks becomes very, very important as you kind of mature with these tools and start to develop your own modeling standard to support your specific application. Okay, so after we've made sure that the model conforms to our modeling standard, the next step is verification. Okay, and again, this is, if we remember that big red bar of value that we saw on the left of that ROI slide, this is really the step where that's achieved. And it all comes down to the fact that unlike a paper document where we had to do verification by review, because Simulink models are executable, we can now do verification by simulation. All right, so let's talk through a little bit exactly how we're going to achieve kind of all that value. So the idea of this step is that we have, based on our textual requirements, some number of test cases, and those test cases include inputs and expected outputs. So what we really want to do in this step is execute those test cases against our model and compare the output of the model to those expected outputs based on our textual requirements. Now, there's a lot of different ways that you can do this in the MathWorks environment. There's tons of ways to kind of automate batch jobs of testing and all that kind of stuff. Most of our customers have already kind of figured out a way that they like to do that, and that's fine. My only suggestion specific for a workflow like this is whatever you have done, kind of wrap that up inside a Simulink report generator template. And the reason for that is so that when you're done executing all of these test cases, you also automatically get out a report that shows the results of all of those test cases. Because again, reporting is such a key aspect to a workflow like this. All right. So again, that's about kind of executing and automating the execution of your test cases. All right. But then the question always comes up when we're testing, how do you know really when you're done testing? And so the third feature of Simulink verification and validation is the measurement of model coverage. And I actually suggest that model coverage is the best metric that we have as far as testing completeness. All right, and I'll quickly talk through an example. So imagine that you have a bunch of requirements, and for each requirement you have at least one test case. And we execute these test cases against the model, and in all instances, the model gives us the same as our expected output based on the requirements. So in some projects, some might consider that our testing at the model level is complete. However, I would suggest that you want to measure model coverage, because let's say in that instance, we passed all of our tests, but we only got 60% model coverage. To me, that's a big red flag. Right? Because now I have to ask myself, what is all that stuff in the model that's part of that 40% that wasn't covered? And if you think about it, there's really only a couple of things that can indicate. Right? So the first is that functionality in the model is unnecessary. So it's unintended functionality, and we need to delete it. Right? So that's one possibility. Another possibility would be that functionality in the model represents valid derived requirements. And so maybe in that case, there's a little bit of documentation that we need to do. All right. Another possibility might be that, that functionality that's in the model, it wasn't covered, but we know it's necessary for the model to work correctly. And so maybe in that case, what's actually missing is textual requirements. So it could be that that's indicating that we're missing some requirements. Another possibility would be that we didn't access that functionality. We traced that functionality back to a requirement, but for some reason the test case for that requirement didn't access all of that functionality. So in that case, maybe we need the functionality, we have the requirement, and what's missing is a test case. So the point is that by measuring model coverage, that's how we can actually achieve this more in-depth analysis of our requirements. And recall that we're doing this at the model level or kind of in the requirements and the design phase. And if you compare that to a more traditional software development process, you typically don't get to do that kind of testing until you're in the testing phase, after design, after coding, after implementation, right? And so it's by doing all of that checking so much earlier, right? And we saw that the earlier we find errors, the cheaper it is. By moving all of that testing earlier to the design phase, that's how we actually achieve that big red bar of value on the left. We're finding all of those errors in our requirements much, much earlier than you possibly could in a more traditional software development process. So that's what this step of the process is really all about. Now, this step also provides us the opportunity to start to do some more advanced and in-depth verification if we choose. And this is where we start to get into kind of the application of formal methods. So for example, when we run those test cases against our model and we get the right output, we know that our model is behaving correctly for that one specific set of inputs. The question then becomes, how do we know the model is going to give us the right answer for every possible combination of inputs? And again, there's two ways to go after that problem. We could try to come up with all of those possible scenarios, which we don't have time to do. The other is using a tool like Simulink Design Verifier. We could attempt to do what we would call, say, property proving, where you could give that requirement some kind of mathematical meaning, and then in some cases we can do that closed form proof to show that the model will always exhibit that behavior. There's also some other types of analysis that we can do with Simulink Design Verifier, such as design error detection, where we look for things like data type overflows or potential divide by zeros, or detecting dead logic. Best case of that is example of that is something like an unreachable state in state flow. Simulink Design Verifier also gives us the capability to do automatic test vector generation for coverage. So that plays back into that idea of measuring model coverage. The scenario there would be, let's imagine we ran our requirements-based tests against our model and we got 95% coverage, and we can't kind of figure out by inspection what those last one or two test cases that were missing are that would give us 100% coverage. So the recommended use case would then be use Simulink Design Verifier to automatically generate those last couple of test cases we need to get to 100% model coverage. It's then, of course, up to the engineer to look at those test cases, which are just going to be inputs, and understand what the physical meaning of those is, relate those back to a requirement, and then based on that requirement, come up with the expected output, so that we could then run that test case against the model again and check if the output of the model matches that expected output. So the recommended use for test vector generation in a workflow like this is really to assist us in getting all of the functional tests that we need to achieve 100% model coverage. Again, it's just important to understand that it only gives us those inputs. It then has to be up to us to understand what the physical meaning of those inputs is in order to properly be able to treat those as requirements-based tests. So again, that's kind of some of the more advanced techniques that we can use for verification at this step. All right. Now, once we're done verifying the model against the requirements, the next step is automatic code generation. And so for this, we're going to use Embedded Coder. So Embedded Coder supports the generation of C or C++ code. It's more common that in a DO178C type of workflow, people tend to work with C code. You can work with C++. Our Embedded Coder will actually stick to what's considered the safe subset of C++, which is suitable for something like a DO type workflow. So just keep that in mind. Now, part of the code generator, part of Embedded Coder, actually includes traceability from the generated code back to the model. So when we generate code, we'll include comments in the generated code that are the block names. And you can click on those comments and it'll navigate you from the code back to the model. Likewise, once you've generated code, you could right-click on any block in the model, say navigate to code, and it'll highlight all the lines of code that were generated because of that block. So you actually get this kind of bidirectional traceability from the code to the model just as part of the automatic code generation process. Now, it's also important to note that if those Simulink blocks were linked to textual requirements using the requirements management interface, then when we automatically generate code with Embedded Coder, we'll also include in the comments of the code the text of those requirements. So the result is that you actually get traceability from the source code all the way back up to the textual requirements for quote-unquote free, as long as you put the effort in to link the model to the textual requirements. And in the end, for a DO type of process, that's exactly what we need to show. We need to show traceability from the source code back to the requirements. All right. Now, I also mentioned Simulink Code Inspector because Simulink Code Inspector also provides traceability between the model and the source code. However, it actually does it with finer granularity than Embedded Coder. So Embedded Coder can trace every functional line of code back to the Simulink model, but it's kind of limited to granularity at each functional line of code. Simulink Code Inspector can kind of go to the next level of detail in that it can actually trace every single operator within a line of code back to the model. So that's important to note, and we'll talk about kind of the rest of what Simulink Code Inspector does in a second. All right, so once we've automatically generated the code and we've traced it back to the model, the next step is conformance to standards. And this is your very typical, does my code conform to my coding standard? In a DO 178C process, it's very common that you want the generated code to conform to the same coding standards as any handwritten code that you might be using. And so that's perfectly fine. And again, that's where you get into that exercise of determining what the right usage of Simulink blocks and code generation settings are to make sure that the generated code comes out looking the way you want. Now, as far as actually checking that the code conforms to standards, so again, in some cases this is still done by manual review, but we want to try to automate as much as possible. Polyspace actually includes the MISRA guidelines. Those are kind of built into Polyspace, and Polyspace can do the same static rules checking of source code against these coding standards. So Polyspace has MISRA C, it has MISRA C++, it has the MISRA CAEGC, so the automatic generated code standard implemented as well. So the idea is that using Polyspace, we can actually automate the checking of our source code against such a coding standard. Now, many times companies or projects have their own specific coding standard. A lot of the times that I've worked with customers, we actually find that most of those can actually be expressed as some subset of the MISRA C rules, but in some cases they can't. And so like the extra capability of Simulink V&V in the Model Advisor gives you the capability to write your own custom rules. Polyspace now actually includes the ability to write your own custom coding rules as well. So depending on your coding standard, that may or may not be very important to you. Now, once we make sure that the code conforms to standards, right, the next step is verification of the source code against the model. So again, this is typically our code review process, all right? And this is where Simulink Code Inspector comes in. So Simulink Code Inspector is one of the MathWorks newer tools, and it's specifically designed to automate code reviews. So what it is essentially an independent check on the code generation tools. So it looks at every mathematical operator in the model and verifies that it was properly implemented in the source code. All right, so again, being able to eliminate manual code reviews is a huge time and money savers. So Simulink Code Inspector is very key in these types of workflows for preventing you from having to manually review the automatically generated code. All right, so once we've completed the verification of the source code, the next step is kind of verification of the object code. And this typically takes on a couple different flavors. So the first thing we have to think about is the compiler. So especially in a DO 178C type process, there's a difference between executing compiled object code on a local machine and executing compiled object code running on the target processor. It's easiest to get certification credit for testing object code on the target processor. So again, if we can kind of enable test case reuse into that environment, that's going to save us a lot of time and money. And so that's actually part of what Embedded Coder allows you to do. All right, so you see I call out this pill mode. So embedded coder supports what we call software in the loop or SIL testing, as well as processor in the loop or pill testing. And essentially what this is it's just a way that from within Simulink, when you press play, you can choose whether you want to be executing Simulink blocks or whether you want to be executing the compiled generated code running locally, that's SIL, or the compiled generated code running on a target processor, which is pill, communicating with your IDE and then talking to the actual processor. Okay, so the idea here would be for a DO178C process, we'd really like to take advantage of this pill mode because now we're executing the compiled generated code on the target processor. And so that makes it easy for us to take certification credit for this testing. Now, anytime we talk about testing, the question has to be, well, which test cases are we using? All right, and so we can see that there's kind of two sets of test cases that you would want to consider. All right, so in a DO178C type of environment, typically we would consider the textual requirements to be high-level requirements and the model to be low-level requirements. So this step would be verification of the code against low-level requirements. All right, and the last step would be verification of the code against high-level requirements. The verification of the code against low-level requirements, what we really want to do here is prove functional equivalence between the model and the code. And the easiest way to do that is have a set of test cases that gives us 100% model coverage. If we then execute those against the model and execute those against the code and get the same answer, then we have shown the code to be functionally equivalent to the model. Now, recall earlier that I said ideally what we want to be able to do is actually get 100% model coverage based on our requirements-based tests, right? Our high-level requirements-based tests. If we can accomplish that, then we can use those test cases and this verification of the code against the low-level requirements actually becomes the same activity as verification of the code against the high-level requirements because it's the same test cases that we're using in both of these. So that's actually a significant value right there, kind of exempting ourselves from having to do this traditional kind of very low-level testing and being able to just concentrate on our high-level testing because we made sure that our high-level tests were completely covering our design. Okay. Now, just like before, there's a lot of different ways to automate batch jobs of tests. I don't really care which one you use. I just recommend that you call that from within Report Generator, again, so we can get that test report out when we're done. The other thing I would recommend is integrating with a third-party code coverage tool. All right. In most cases, a set of test cases that give you 100% model coverage will also give you 100% code coverage. However, that's not guaranteed. There are some situations in which model coverage and code coverage can be slightly different. And so, especially because DO178C, depending on what level you're trying to accomplish, so DO178C level A would require that you show 100% MCDC coverage of the code. We really want to kind of measure code coverage anyway to meet that requirement. It will also give us a good indication of whether code coverage and model coverage are equivalent. If they're not, again, this is a good opportunity for us to use traceability in the source code back to the model to understand what model construct it was that might have created that discrepancy, and then authoring a new modeling rule to kind of revise how we maybe are happening to use that particular model construct to make sure that we don't see that coverage discrepancy in the future. All right, so I'll actually show an example of kind of how we can integrate with third-party code coverage tools as well. The last step here is another use of polyspace. So we talked about polyspace briefly as a static rules checker. The much bigger and more important part of polyspace is its formal methods analysis capabilities to prove the absence of runtime errors. So this is a very important part of software safety, basically proving that there's no chance that your code could have a runtime error. Now, in a workflow like this, not only is it important to do that kind of analysis, but one of the nice side effects that you get is because of how polyspace actually does the runtime error analysis, it actually calculates the theoretically possible range of every variable at every operator in your source code. So what that means is that you can actually take those ranges and use that and exempt yourself from having to do kind of the traditional boundary value testing that you might otherwise have to do. And so this actually leads us straight into the conversation about tool qualification. So there's some differences in DO178C as far as tool qualification from DO178B. DO178B had two classes of tools, development tools and verification tools. DO178C has three classes of tools, Class 1, Class 2, and Class 3. So Class 2 is this class of tools that says, these are tools that are essentially verification tools, but can exempt you from downstream testing. And that's exactly what Polyspace can do for you, in that it can exempt you from that downstream boundary value testing. So the MathWorks has actually updated our DO qual kit to perfectly handle the fact that Polyspace can be qualified as a Class 2 tool. Now the rest of the tools that you see in here that have asterisks, these are also part of the DO qual kit, and these can be qualified using the qual kit as Class 3 tools. So I won't go into kind of the details of how we pick which tools are part of the qual kit. I'll actually go through that in a bit more detail as we actually use each tool in the follow-on webinars. I also want to quickly take this opportunity to introduce the model that we're going to use in all of the follow-on webinars. In this case, we have kind of a system level model that we can take a look at. And then for the software development, we're actually going to focus on just one component of the system level model. So the larger problem that we're trying to solve is actually to build a system that uses a motor, a rotational motor, and a webcam to develop a system where we can rotate the motor to rotate the webcam to follow a green ball and keep a green ball centered in the frame of view of the webcam. Right? So, without getting into the very heavy systems engineering type activities where we would define architectures and components and stuff like that, for this particular example, we've kind of broken this larger problem into 4 separate subsystems. So the first component is the actual getting the data off of the webcam. Okay. The second component is once we have that image, doing some kind of image processing to determine if there is a green ball within the image that webcam has captured. So that's what's going on in this image processing component. The logic controller component says, given the image and the position of the green ball in the image, decide whether it is a green ball and whether we should be trying to track that green ball. If we are trying to track it, what should be the angle command to the motor to keep that ball centered in the field of view? Otherwise, there's some basic error checking. So if the ball is not in the field of view, what should we be doing with the motor to point the camera in what direction do we want to point it? And then the last component would be given whatever computation we do make as far as what angle the camera should be at to keep the ball centered in the frame of view, we then have a closed loop motor controller to actually do the closed loop motor control and do the position commands and position control to turn the camera and hold the camera at the angle that we want. All right. So for all the follow-on webinars, we're going to be focusing on this one component, which is the logic controller. Okay, so if I open this up, you'll see this is where, again, we kind of make decisions about is the ball in the field of view? If it is, how should we be commanding the camera to keep it in the field of view? All right. So I just want to introduce this because we're going to focus purely on this section, but it is worthwhile to note that this is simply one component of a larger system. And in fact, this is a large hybrid system because the component that we're going to focus on in this webinar series, we're planning on generating embedded software for. The component of this system that is doing the image processing, we actually intend on implementing that on an FPGA. So there's a whole nother conversation to be had about how Simulink models can be used to generate VHDL and Verilog, and how this same or a very similar process that we're going to discuss in these webinars could be suitable for something like a DO254 type of project where we're developing complex electronics and hardware. So that's it for the introduction. Again, the idea here was just to kind of introduce this workflow, kind of tie it back to the value statement that a lot of our customers are already seeing in implementing model-based design in DO178 environments. So hopefully that gives you some introduction into model-based design for DO178C software development. Again, if you're interested, please feel free to view the following webinars to actually see the tools in use and get a much more detailed view of how our tools can help you in this kind of process. Thank you.